In this video, I will show how to control a servo motor using a potentiometer. This example will behave similar to that of the knob Arduino example. However, unlike the software-intensive Arduino example, I will implement this example using the core-independent peripherals featured on PIC microcontrollers. At the end, I'll compare the program memory of the PIC-based implementation versus the Arduino knob example. The material used in this video will consist of a PIC 16F18855 express board, a Tower Pro MG996R servo motor, and the MPLAB X IDE. I have a copy of this servo's datasheet opened. Looking at the overview paragraph for this servo motor, I can see that the actual range of motion for this servo is about 120 degrees or 60 degrees in each direction as opposed to a full 180 degrees. This servo requires a PWM signal with a 20 millisecond period. In order to achieve the minimum position, the high pulse of the PWM signal needs to be about 1 millisecond. Additionally, to achieve the maximum position, the PWM signal needs to be about 2 milliseconds. To begin setting up this project, I have the MPLAB X IDE open along with the MPLAB code configurator. In this project, I will read analog values from the onboard potentiometer and feed that value to a timer to control the servo motor. Therefore, I will start by adding an ADCC peripheral. I will enable continuous operation so that I will only have to start the ADC conversion one time and it will continue to sample on its own. Additionally, I will change the result alignment to left. I will explain why this left alignment is important later on in the video. Next, I'll go to the pin manager and lock the analog input pin of the ADCC to RA4. Pin RA4 is connected to the potentiometer on the express board according to the express board pinout. Lastly, I'll go to the pin module and rename this pin to something easier to remember. Based on this servo's datasheet, the correct PWM for this servo has a period of 20 milliseconds. The high pulse of this PWM signal needs to vary from 1 millisecond to 2 milliseconds in order to achieve the minimum and maximum servo positions. I'm going to use 3 different timers in combination with a configurable logic cell peripheral to create my own PWM generator. It should be noted that I could simply use a PWM peripheral to generate the required signal. However, through using these timers, I will be able to create a higher resolution PWM signal. Timer 2 will operate as the period timer. Every 20 milliseconds, it will trigger the other 2 timers to start. Timer 4 will produce a 2 millisecond pulse every time it is triggered. And timer 6 will generate a user-defined pulse which will vary based on the potentiometer readings. The 2 millisecond signal of timer 4 will be inverted and ANDed with the 0 to 1 millisecond signal of timer 6. To begin setting up these timers, I will first change my internal system clock to 8 MHz. Next, I'll add a timer 2 peripheral to my project. Additionally, the clock source needs to be changed to low frequency internal oscillator. I'll need to change my prescaler to a 1:4 ratio so that the timer period field is able to operate at 20 milliseconds. It should be noted that I could use many different combinations of clock source and prescaler which would allow for a timer period of 20 milliseconds. However, I chose this particular combination because MCC does a calculation for you which will tell you the actual period that will be output based on your settings. With this combination, I get an actual period of 20 milliseconds exactly. However, when I change my prescaler to a 1:8 ratio, for instance, I can see that my actual period is not exactly 20 milliseconds. This can potentially cause undesired results for my servo. This calculation that MCC does for you helps ensure that you will be able to control your servo to its exact specifications, which is extremely helpful. Next, I will add a timer 4 peripheral, which will produce a 2 millisecond pulse. To do this, I will change the clock source to FOSC divided by 4. The prescaler also needs to be changed to a 1:16 ratio to allow for a 2 millisecond period. Once set, I'll change the timer period to 2 milliseconds. I'll also need to change the control mode to monostable mode. In this mode, the timer can be triggered by an external source. When triggered, the timer will generate an on time for the duration of the user-defined period. Additionally, I'll set the external reset source to timer 2 post-scaled. Next, I'll add the last timer, timer 6. This will have a similar configuration to timer 4. I'll change the clock source to FOSC divided by 4. Next, I'll change the prescaler to a 1:8 ratio to allow for a 1 millisecond period. Now I can change the period to 1 millisecond and set the control mode to monostable. The reset source will also be changed to timer 2 post-scaled. Again, this servo's period value will change so that the duration of the high pulse going to the servo will always be somewhere between 1 millisecond and 2 milliseconds. As mentioned previously in this video, the 2 millisecond signal of timer 4 will be inverted and ANDed with the 0 to 1 millisecond signal of timer 6. Therefore, I'll add a CLC peripheral and change the first input to timer 4 and invert its signal. Next, I'll change the second input to timer 6 and route it so that it and timer 4 are ANDed together. The output of the CLC will be tied to pin RC7. This will be the PWM signal that will be given to the servo motor. I have now finished all of the configuration needed to control my servo, so I will go ahead and click the Generate button. Inside of the main.c file, I will call the ADCC start conversion function, which can be found in the ADCC.c file. I will paste this function right before the while one loop. This will initialize the ADCC. If you can recall towards the beginning of the video, I set the ADCC in continuous operation mode. Therefore, now that this ADCC start conversion function has been called, the ADCC will continue to sample without being triggered by software. Inside of the while one loop, I will now call the timer 6 period set function. This function can be found within the timer6.c file. Looking into the ADCC get single conversion function inside of the ADCC.c file, I can see that an ADC result is returned, which is a combination of the ADC high result shifted to the left by 8 bits and the ADC result low. If you remember in the earlier parts of this video, I changed the result format from right to left. In the datasheet, it specifies what both ADC result high and ADC result low look like with each configuration. Since I left aligned the result, this means that by passing only the high ADC result to the timer period, I am passing only the 8 most significant bits. This will be a value of 0 to 255. This works perfectly since timer 6 is an 8-bit timer. Therefore, I'm going to pass the ADC high result value to the timer 6 period set function. When I make and program my device, you can see that my servo moves as I turn the potentiometer. This project successfully replicates the knob Arduino example. However, through this core-independent implementation, only 336 bytes of program memory was used, while the Arduino example uses 2,758 bytes to accomplish the same goal. Since this implementation is done through hardware, the application still has 98% of its program memory remaining. This same technique can be used to produce core-independent LED drivers or any other custom peripherals that you might need for your application. For more information about how these core-independent peripherals can be used within your own projects, please see the link provided in the description below.